Okay, let me start writing some examples of some sets. Let's suppose we have A equal to 1, 2, 3, apple. B equal 1, 2, apple. D equal to 1, 2, 3, 4, 5. K equal to 1, 2, apple, 3, 1, and 2. Let's suppose that L is this set, and let's say that M is 1, 3, 5, and 7. Something that we have is that when we are thinking about sets, this symbol, these braces, the comma, and these braces like this can be thought as reserved symbols. Right? And the reason is that every set starts with that symbol and it ends with this symbol. And everything that is between this symbol and a comma is considered to be an element. Like here, the 1 is considered to be an element, right? Or everything that is between the comma and that is considered to be an element. Like this is considered to be an element. Or everything between the commas is supposed to be an element. We're going to write, for example, for set number A, we're going to write 1 is an element in A. And we are going to abbreviate this by writing 1, and we're going to use this symbol. It's an element in A. And for example, we have that 4 is not an element in A, and we are going to abbreviate this by saying it's not an element in A. Then we have this notion of being an element. That means that we have this other symbol here, which is being an element and not being an element. Let me keep going with definitions. We can compare two sets. Comparing sets. Let me just write this. Comparing sets E and F. Then this is a relation between two sets. We can say something about two sets. Let me write the definition. Definition. We say that E is a subset of F, or E is included in F if every element in E is also an element in F. And when this happens, we will write that E, this is the symbol, included, or E is a subset of F. As an example, we have that B is a subset of A because every element in B, 1 is an element in B, is also an element in A, 2 is an element in B, is also an element in A, apple is an element in B, is also an element in A. If you can check that every element here is an element there, then we can type this. We use this symbol, for example, for this particular example, this symbol will mean it's not a subset. And the reason A is not a subset of B is because this proposition is false. every element in E is also an element in F. Here, not every element in A is an element in B. Why? Because we have that 3 is an element in A and 3 is not an element in B, right? Then we will write this also, this symbol. Let me keep track of the symbols that we are using. This is included or is a subset. This is not a subset or is not included. Remember that we are also taking this as restricted symbol. A comma is a restricted symbol, and let me just forget about the comma. A comma is a restricted symbol, and this braces like that is a restricted symbol. It has a meaning. An interesting observation is that this set here is a set with not elements. Remember, it just starts with the braces and it closes the braces and there is nothing in there. This one is called the empty set. And one of the properties of the empty set, keeping in mind this definition, is that for every set D, for every set E, the empty set is contained in E. Why I can show that this is not false? To prove that this is false, I will have to show an element that is here and is not there. But there are no elements there. That means that for me it's impossible to show that this is false, and for that reason it's always true. Then I can say that the empty set is a subset of A, the empty set is a subset of B, the empty set is a subset of D, and for the empty set is a subset of the empty set, and in general the empty set is a subset of any set. Okay, we are thinking about comparing sets A and F. Then if we have two sets, then we can say that one is containing the other or one is not containing the other. Let me just write another definition. And this definition says that E is equal to F if E is containing F and F is contained in E. That's the definition. We say that two sets are the same if these two things happen. Notice that as an example, write the example here. Example of this definition, we have that the set A and the set K are the same. A is equal to K. A is equal to K. Why? Because every element in A is an element in K, and every element in K, if I pick an element here, 1, 2, or apple, or 3, or 1 or 2, is an element in A. Then, for that reason, when we are considering sets, then the order doesn't matter. And if you repeat some elements, it doesn't matter either. One observation is that usually when we refer to the number of elements of a set, we refer to the number of different elements in that set. For example, how many elements are here in K? We have 1, 2, 3, 4, and we don't count these 2 because they are repeated. Okay, then we have this definition of being equal. This is about comparing sets, comparing two sets. Let's see what type of operations we can do with sets. Let me write operations. Then we have the union. And the definition is that E union with F is the set that has all the elements in E and all the elements in F. As an example, if I do A union with M, if this is A and this is M, then A union with M is 1, 2, 3, apple, and I will continue with the elements in M. I don't need to write 1 because, as I mentioned here, you don't need to repeat the elements. 1, 3, the 5, I need to include the 5, and the 7. We have also the intersection of two sets. That intersection. And we denote that like this: A intersection with F, and this is the set that have the elements that are in E and also in F. Then in order to be part of this set E intersection with F, that element has to be in E and also it has to be an element in F. As an example, we have that B intersection with, let's say, with M are the elements that are in both. Let's say 1 is in both, then we have 1 is there. 2 is in B, but 2 is not in M. Then we have that 2 is not in the intersection. And apple is in B, but apple is not in M. Then in this case, the intersection is just this set. What would be the intersection of A intersection with the empty set? Then in this case, an element is here if it is in A and is in the empty set, but the empty set has no elements. And for that reason, no element can be in the intersection. Let's continue with the Cartesian product. In order to define the Cartesian product, we need to define the notion of an ordered pair. For an ordered pair, we're going to denote an ordered pair, something that starts with a parenthesis. It has an element here, and it has another element, and it closes with a parenthesis, and it has a comma. Then an example of an ordered pair would be like A1, right? This is an example of an ordered pair. One of the differences between an ordered pair is that when you consider this ordered pair, this is considered to be different from the ordered pair 1A, right? Two ordered pairs are the same if the first entry is the same and the second entry is also the same. We can also define something that for 3 elements, ordered triplet. In this case, we're going to have 3 elements. Like you start with a parenthesis, there are 2 commas, and we have like A, 1, and 5. And the rules are that 2 ordered triplets are the same if the first entry is the same, if the second entry is the same, and their third entry is the same. And in general, we can define n-tuplets. And they are made out of n elements. And the property is that 2 n-tuplets are the same if their first element is the same, if their second element is the same, and so on. Then for the Cartesian product of 2 sets, let's say E, the notation is E cross F. This is the set of ordered pairs, and you can, let's say, X and Y. But I forgot to mention, but this means such that sometimes we use this, or sometimes we use just 2 dots like that. both of them means such that X is an element in E and Y is an element in F. This is the definition of Cartesian product. Then if I do the Cartesian product of A Cartesian product with B, then what are the elements here? Let's start writing the elements. We have 1 is there, right? Because 1 is here and 1 is there. The ordered pair 1 1. The ordered pair 1 2 is also there because 1 is in A and 2 is in B. We have 1 apple is there. We also have 2 1 is there. We have 2 2 is there. 2 apple is there. And then 3 1 is part of the Cartesian product. 3 2 is part of the Cartesian product. And 3 apple is part of the Cartesian product. And then apple 1 is part of the Cartesian product. Apple 2 is part of the Cartesian product, and apple is part of the Cartesian product, and then we end this set like this. Notice that here the number of elements of A cross B is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You can check that in general, the number of elements of A cross B is equal to the number of elements in A times the number of elements in B. 4 times 3 is 12. Then we have the Cartesian product. E1 Cartesian product with E2 Cartesian product with EK. Then in this case the Cartesian product would be the set of n-tuples. I erased it. N-tuples, let's say x1, x2, sk, such that the kth entry, the ith entry, is an element in EI. Let's do an example. Let's suppose that we have this set 1, 2 cross A, B, C cross with apple and a square. What would be the Cartesian product of these three sets? 1 A apple, 1 A square, 1 B apple, 1 B square, 1 C apple, 1 C square, and then 2 A apple, 2 A square, 2 B apple, 2 B square, 2 C apple, 2 C square. You can check that the number of elements in this Cartesian product is equal to the number of elements in this set times the number of elements in this set times the number of elements, and so on until times the number of elements in this set. In this case, this Cartesian product is supposed to have 2 times 3, 6 times 2 is 12. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We can do also the Cartesian product of, let me finish by doing the power of a set. Then let me start with this. Let me continue with this definition. The power of a set E is the set of all subsets of E. And then as an example, we have that the power of the set B, let's say the power of the set B, we denote it like this, is the collection of every possible subset of B. Then we have the empty set, which is a subset of B. What else is a subset of B? The set with only one element. This set, what else is a subset of B? We have the set whose only element is 1. The set with this only element 2, and this set. Right? You can check that this set, right? You can check that 3 is a subset of B. Right? And then let's keep going. And then we have the set with elements 1 and 2. The set with elements 1 and apple. The set with elements 2 and apple. And the set with elements 1, 2, and apple. And then we close the power set. Notice that this power set has what is between this and the comma. We have one element, 2, 3, 4, 5, 6, 7, 8 elements. In this case, power of B has 3 elements. In general, we can check that if E has k elements, then the power of A has 2 to the k elements. And let me do an easy example about this. If we have that, let's compute the power of the set 1 and A. Then this set is supposed to have 4 elements, because in this case, this set has 2, and 2 to the 2 is 4. These elements are the empty set, the set whose only element is 1, the set, this set, and this set. Then we have 4 elements in the power of this set. Let me finish by extending this list of symbols that we have defined. We have defined the union of 2 sets. We have defined the intersection of 2 sets, the Cartesian product of 2 sets, and the power set of 2 sets, and also the equality of 2 sets. Please do these problems.